Okay, good afternoon, everybody. It is our pleasure today to welcome Laurent Masse from Laurent Masse. I thought there was an accent, no accent. From CEA, so he comes from Commissariat à l'énergie atomique, énergie renouvelable, alternative et renouvelable. Merci. He made a PhD. It was last millennia at Université Marseille on fluid mechanics, under the supervision of Pierre Calvin. Paul Calvin. And after that, he made a short stay at Cadarache before joining the CEA for a couple of 12 years, 13 years, working on the laser megajoule. And then you spent a certain moment at Laurent Masse at the National Ignition Facility, working on the lasers there. You will explain to us today how the first fire of this laser worked, something like 12 years ago, and how progress was made until the recent event that will be the center of your talk today. You came back to France at CEA 1 year ago, again at CEA Dam, to go on working and making use of your experiment for the laser megajoule and other laser facilities in France and Europe. So thank you, Laurent, for having accepted our invitation, and now it's your time.
Thank you, Riyad, and thank you for the invitation. I'm really honored to speak here, especially about this topic. So as you said, I'm going to talk about the recent breakthrough in inertial confinement fusion. And to start with, I'm going to talk about simple things. So last August, it was the 8th of August, you could have found this on the website of the Laurent Masse National Laboratory. They were saying, okay, National Ignition Facility experiment put researcher at threshold of fusion ignition. So it was nice. But a few days after that, you could have found some paper in a scientific paper in Nature, for example, or Physique today, talking about this result. And very soon after that, even the press talked about that in the New York Times. Laser fusion experiment unleashes an energy burst of optimism. And same for France. In Le Monde, you could have found fusion nucléaire, une avancée historique réalisée par un laboratoire américain, and in all the paper in Europe. So it seems that it's a big event, and it's not really soon that you can find some paper about in the press talking about physics. So it's sufficiently interesting that you can stop and say, okay, maybe it's happening something, so we need to understand what's going on. But if you read all these papers, it's really hard to understand what really happened. What does it mean? So we got ignition, you talk about ignition, you kind of unleashes energy burst. What does it mean? Plus, it was really a pretty successful year because in February of this year, China, with the Tokamak East, we are talking about getting new record. They were able to get 120 million degrees in the plasma during 17 minutes, which is super large, and that's a record. And the same, they got 70 million for 70 minutes and 120 for 5 minutes. So it was really a big step. And you can find in this article in Le Monde, JET broke a new record recently. It was in March, I guess. And for the first time, they got 59 megajoule in plasma during 5 seconds. So it's new record in fusion, but it's more and more confusing. What does that mean, all these results? You have numbers everywhere. And there is another result. It's coming, and it's pretty nice. That's the first time that a company, 100% privately funded, realized a plasma of 100 million of Kelvin. That's the first time, and they are going really fast. They were really a young company, and they just got this result really fast. So the idea of this talk, which is basically M2 level, as Riyad asked me, is try to understand what really happened and what all these things mean, and how these results compare to each other. That's basically the idea of this talk. So, yes, that's what I'm going to talk about. So, yes, start simple with basics, so fusion reaction and different ways to get them. The Icf fusion, so inertial confinement fusion scheme, and what those results I was talking about represent and what really is ignition. When you talk about ignition, what is ignition? And why is so difficult? Why it's such a big deal? What we are talking about this thing? How did we get there is what Riyad was saying, so how we incrementally improve our understanding to get the last result and what are the next steps. So let's start with the basics. So it's really simple. Just say that you want to start some nuclear reactions. You want to make some combustion just like you burn something, like you burn your barbecue or something. So if you want to create a reaction which is exothermic with nuclei, you need to there's a pointer somewhere, okay. Oh. Ok. Au centre. Ah oui, ok, j'ai vu. Okay, sorry about that. Okay, so yes, so you need to find some initial elements for which the sum of the mass of the initial elements are larger than the sum of the mass of the final element. And if you get that, you're going to have some exothermic reaction. And it's actually interesting to look at the binding energy of one nuclei. So the binding energy is just the defect of mass, delta m, times the square of the light speed. And the defect of mass is just this simple expression. It's just the sum of the mass of the proton and the mass of the neutron inside your atom, subtracted by the mass of the atom. And that's exactly, basically, the energy you need to give to create this atom. So this is the binding energy, and this is a plot of binding energy per nucleon for each element. And it's interesting, so it's made in two parts. You have the right part, so you want to start with, again, as I was saying, you want this Q, delta B, if you want, to be larger than 0. So in this part, you have the fission. So you start with a large atom, and you decrease the size of it, and you get energy. So the fusion is on the other side. That's simple. So you start with a light atom, you make a fusion, you make something bigger, atom bigger, and the defect of mass gives you some energy. That's fusion. That's what we want to do. Okay. So how do you get this reaction? How do you force these atoms to fuse? You need to go through the Coulombian potential, because two nuclei are positive and they don't want to be together. They don't want to fuse at the first step. So you need to go through this Coulombian potential. And the Coulombian barrier makes high temperature necessary for example, DT thermonuclear fusion. I'm going to talk about that later. Hopefully, you have quantum mechanics on your side, because this potential here is on the order of 1 MeV, which is super large. So thanks to the quantum mechanics, you can go through this Coulombian potential using the tunnel effect. And thanks to that, you don't need 1 MeV energy, you just need few keV, which is sufficiently large, but it's good for us. And actually, that's the reason why, at the beginning, people were thinking that the temperature of the sun were much, much larger than it is. It's because of that. They didn't know about the tunnel effect. Okay. So the thing is, the tunnel probability is inversely proportional to mass and atomic number. So you have more chance to go through this potential, Coulombian potential, if you use a light nuclei. So lighter you can do is hydrogen. So it's simple. You just take hydrogen and you try to fuse. That's the simple thing you can do. And the thing actually, so you can use some isotopes of hydrogen, and that's basically what I'm showing you here. So you have two atoms. So the first one is just what we call a deuterium. So it's a proton and a neutron. and tritium, which is a proton and 2 neutrons. And so when you combine these two guys, D plus T, so deuterium plus tritium, you create an alpha particle, which is basically a helium atom and just a neutron. And you get energy from there. So that's what we would like to do. So what are the cross-section, what are the chances to get this reaction? So you can use the cross-section of the reaction I was talking about, and you Maxwell average this fusion reactivity and get what we call the sigma V, which is depend only on the temperature, and that give you a little bit of an idea of what are the chances that you can get this reaction. And you can compare different reactions. So again, I was talking about hydrogen isotopes, so you have D plus T, maybe you can do D plus D, or you can do D plus helium-3, for example. But you see that the best one, the easier one, is clearly this one. So that's the reason why everyone is using D plus T. It's the best. It's probably not the best if you want to create a power plant, because T is not free. So you can't find deuterium in salt water, in seawater. But tritium, you need to create tritium, and it's not free. So you want to find other ways to get the T, but that's another question. Okay, so that's our reaction. So now what we need to get this thing going. So you can write this down. So that's the reaction rate. Basically, that's the number of reaction per unit time and per unit volume. So, and it is the density of material, and that's just the density of the atom 1 times the density of the atom 2, so deuterium, for example, and tritium, for example, times the sigma V I was talking about, which is just a function of temperature. From that, you can create a time for fusion. That's basically the time between two fusion reactions. And that's this guy. So at the beginning, people were thinking, okay, that's easy. So you can just launch some deuterium onto tritium, and you can make some reaction, and that's going to be easy. The thing is, when you do that, you are more likely to make some collision, elastic collision, than reaction. And you can't burn something like that. So you really need to have high temperature and maintain your system. So that's exactly this reason. So you have this time of time for fusion, which is much larger than time for collision. And actually, if you want to reach the thermonuclear regime, you need to confine your system. So you need to keep your system long enough after 1, 2, 3 collision to get a fusion collision. You really need to keep that. So that's the reason we are calling that thermonuclear reaction, because you need to keep your system in high temperature. It's not just enough to launch one particle onto another. So you really need to have this confinement time larger than the fusion time. So if you confine your system long enough, you have long enough to get some fusion. And that's really that you need. And this ratio depends on density. It depends on sigma V, which depends on temperature. So it depends on density, on temperature, and time. So that's basically the main ingredient you need to do fusion: time, density, and temperature. Sorry. Okay. So there are at least 3 ways to achieve nuclear fusion. So the one you know is gravitational confinement. That's the sun, or that's the stars, we all know. And if I look at this project, so I was saying density, temperature, and confinement. So you have super large density because you have huge mass and huge gravitational force. You have temperature of 1 keV. So one EV is about 10,000 Kelvin. So 10 keV is about 100 million K. So 1 K is about 10 million Kelvin. And you have super long time, confinement time. So you have the magnetic fusion. So I know that Xavier Garbet came here a few months ago and he was talking about magnetic fusion. I won't talk about that, but it's really similar, and that's exactly what I'm showing you here. So that's a big torr and a big volume. So for the jet I was talking about before, the outer radius of this door is about 3 meters. So yes, so in this big volume you have really small density, so it's 10 to the 8th, 1/10 to the 8th of the solid density, pretty high temperature, 100 million is exactly what I was talking about before, so the 100 million they reached. And you have confinement about seconds, even minutes. And I'm going to focus on this guy, which is inertial confinement. So in this case, you trade time for density. So you don't have much time because the confinement is super small, so it's tens of picoseconds, maybe hundreds of picoseconds if you are lucky. But it's really small. You have about the same temperature, about 10 keV, but you need to reach super high density. So solid density, thousands of density, 1,000 grams per centimeter square. Okay, so this is 2 examples of Icf facilities. So again, Icf is inertial confinement fusion. And so you have the NIF, so which is the laser where they got this nice result. So it's pretty large facility. So this guy is about 300 meters, so it's free stadium football, American football stadiums. There is 192 beams delivering 1.8 megajoule. 1.8 megajoule is just ridiculous in terms of energy. It doesn't mean anything. It's just like what you eat with your steak or your yogurt, or I don't know. But what is impressive is the power. It's 500 terawatts. It's just like you eat your steak and you get the energy from the steak in nanoseconds. So it's just like that. It's just this power, which is just incredible, 500 terawatts. Okay, so that's basically the facility. That's where the laser is amplified, actually, and where the experiment is done is in this little cube. We have another facility in France, and which is not as good as NIF yet, but which is not that bad. Actually, we are second in the world, so not that bad. Far from NIF, okay, but okay. So, and it's basically the same size. So you have a chamber of experiment which is about 10 to 14 meters of diameter, which is super large, and you focus your 192 beams onto a little thing which is about 1 millimeter of radius. That's the craziness of this thing. Okay, so that's the facility. I won't talk about technology and laser. You can do 1 week of work on that, so I won't talk about that. So you have 2 ways to use this laser power to get ignition or to get fusion reaction, because that's what we want. So you can do direct drive, and super easy. You take your little sphere I was talking about before, and you shine your laser onto this little pellet, and that's it. That's super simple. Or you can do fancier, so you can shine your laser inside kind of a little can, a gold can, and this can is going to absorb the laser energy and reflect this laser energy onto X-rays. And this X-ray is going to be a little oven of X-rays, and that's going to be super smooth around the little sphere, and it's going to help the implosion. But that's basically what you want to do. I'm just going to talk about this scheme, because that's the scheme they used to get this result. So I'm going to focus on this thing, but you can find a pretty important community on this direct drive scheme. Okay, so that's just one slide for the indirect drive scheme, just to understand what's going on. So this is the can I was talking about. So it's really a can. It's about 1 centimeter long, super small. It's gold. It's made of gold, and you have 2 holes on the top and the bottom, and you have all the beams coming inside. And the beams are shining inside this can made of gold, and you get this X-ray radiation around a little capsule here, which is about 1 millimeter or 2 millimeter of diameter. So that's a zoom of this, or a slice or a section of this little capsule, this little thing inside this can. And this is what it's made of. So it's a capsule consists of plastic or HDC ablator. So HDC is just a fancy name for diamond. It's nothing else than diamond. It's high density carbon, but it's diamond. But it was too fancy to talk about gold cans, gold all-room, and diamond. So it was too much, so they changed the name. It was better. So you have this ablator, and inside you have your DT. That's the fuel you want to burn. And in this scheme, this fuel is made of two parts. So there's a gas part, with a low density, and a solid part. So solid part is kind of much thinner, but much denser, obviously, because it's DT. I don't know if you know at which temperature DT or hydrogen are solid. It's about 18 K. So it's not that hot. It's super cold. That's the reason why we are calling that cryogenic DT layer. It's a challenge to get this thing done and to get this layer of DT made in this capsule. But that's something we can do. And when you have that and you shine your laser inside your capsule, actually this ablator, this thing, orange thing around this capsule, is what we call ablated. So the X-ray flux is absorbed by this material and vaporized. And the shell is imploding because of the conservation of the impulsion. So it's just like a rocket effect, but you have a rocket everywhere in every direction. So the only way you have to go is inside. So that's rocket everywhere, and you implode. That's the way you do this implosion. So the convergence is about between 20 and 30. So basically it's shrinking a basketball to a marble size. That's basically the idea. So you take a basketball and you shrink the basketball to the marble size. And you need to do that pretty nicely, pretty uniformly. You don't want to push too much on one side or on the other, because that's not going to work. I'm going to show you how that. Okay, so after that, when you do that, you get a kind of a hot spot encapsulated in a dense shell. Okay, I'm just going to show you a little movie just to show you what's going on. So it's a simulation. Yes, it's working. So on the right, you have the laser power as a function of time. So you see that the time is, okay, where are you? It's about 20 ns, so 20 nanoseconds. So the power goes up to 400 terawatts. So I'm going to show you again this movie. Say on the right, on the left, sorry, you have the can I was talking about and the little capsule inside. And you see the laser coming inside the hologram, and you don't see that, but you have some X-ray emission, and I'm going to show you again. And this X-ray emission ablates is what you see here, this little capsule, and at a given time, this capsule starts to implode, and you create your dense and hot little thing. That's what you want to do. Okay, so before going into the detail, I'm going to give you some numbers. What really happened on August of last year, sorry. So that was the can they used. So as I was saying, so 11 millimeters, so it's about 1 centimeter. This is the power as a function of time, so 440 terawatt. And with that, they got 1.9 megajoule of laser energy for 440 terawatts. And they got a fusion energy of 1.35 megajoule. So when I'm talking about energy, it's just the energy of the alpha particle I was talking about, the helium-4 I was talking about, plus the neutron. So they got 1.45 megajoule. The temperature measured, it's not just theory or just paper. So that's the temperature measured. It was 11 keV. It's just exactly what we want to get, okay? And it's about 100 million of Kelvin. So I'll give you some numbers, but don't worry about them. So it's 50 microns, the size of the shell at the end, the hotspot. So the convergence was 21, exactly that was what I was saying. The hotspot pressure, it was about 500 gigabar, which is about twice the pressure inside the sun, to give you an idea. And I won't talk about the capsule again, but this is the gain. So what is the gain? It's super simple. It's just you take the fusion energy you get for your experiment and you divide by the laser energy you get from your laser. And it's 0.7. So basically, that's the reason why, at the beginning of the presentation, Livermore didn't say they got ignition. They said threshold of ignition. But I'm going to show you that it's just a political reason. So the political reason is they agreed with the NNSA or Ministère de l'Armée, I don't know. So with the government that they're going to claim ignition when they're going to get the gain 1. So fusion energy over laser energy equal to 1. But that's just a political definition. I'm going to show you that if you take a physics definition, there's going to be another story. Okay, so exactly what those results really mean. Okay, so to do that, we're going to show you a little model. Okay. Yes, so what really matters is more the regime you reach by those, but than the sheer fusion performances. For example, you can get a capsule bigger and bigger, and you can get more and more fusion just because of the scale. That's not changing anything. So what you try to do is reach a regime, and the regime you want to get is the self-sustained regime. So it's just like you want you ignite your barbecue, so you take a match and you burn your match, and if your match is going down, okay, nothing happened. What you want to do is crack your match, and you start to burn, and you see that your barbecue is starting to burn itself. It doesn't need anything now. So that's exactly what you want to do here. So self-sustained combustion. Okay, so to have a self-sustained combustion, you understand that it's a question of energy balance. So you need to compensate the losses by the gains. And when you get that, so that's an image or a simulation of hotspot ignition. So that's what you get at the end of the implosion. On the bottom, you have the temperature, on the top, density, and you have a kind of hotspot, that's what we are talking about, surrounded by a dense shell. So if you are able to do what we were saying, so you can get ignition, start to have some self-sustained reaction in this hotspot. After that, you can burn all your barbecue. You can burn all your charcoal. You start with something, and after that, you have burn propagation. That's two stages. Ignition, after that, burn propagation. Okay, so if you do a little bit of math, so just an energy balance, it's super simple. So on the left, you have the variation of the internal energy of your system. So what I'm talking about is I'm doing this balance inside this hotspot, so this hot part, okay? So I'm taking this sphere, I'm doing an energy balance inside. So that's the variation of the internal energy, and this guy depends on the fusion reaction. That's just the energy given by the reactions, by the alpha particle and etc. Okay, that's the combustion if you want. You have this one, which is also a gain, but it depends. So that's the PDV work. So, but it's not a solid line, it's a dashed line, because this guy is giving you some energy when you are shrinking your system. So when your volume is decreasing, that's a gain in your system. You're giving energy in your system. So you have your combustion and the energy you're giving to your system by compression. For the losses, this one is still a loss when you start to explode. Okay? When you implode, it's a gain. When you explode, it's a loss. But you have some radiative losses. So because it's super hot, you are doing a lot of radiation and you're losing energy through radiation. So you are losing energy through this guy, and you are also losing energy through just sheer conduction, because you have a hot spot surrounding that something which is cold, and you are losing energy because you are losing through conduction. Okay, so this is your losses and your gains. So you reach ignition when this energy balance is 0. So exactly the same. So you have same wins, same losses. And you are just at the beginning of ignition. This was okay. So that's basically this equation. So you can write down this guy. So we're gonna say, to start with, to make things simple, that this hotspot implodes, so it was decreasing, and it's just here, and it's about to explode. We are just looking at this guy just at the minimum volume. So the volume is not changing anymore because we are stagnating. We're just looking at this time where the volume is not changing anymore. So I remove this part and just this balance. Or you can write, and all these terms depend on temperature, and depend on temperature and what we call ρ, that's the product of the density times the radius. You can do the math, but trust me, that's something like that. It's just a compensation between volumetric gain or losses and losses through surface area. That's the reason why you have this type of formulation. Okay, so if you do that, you can write a curve like that, depending on temperature and what I was calling ρ. Okay, these two, yes?
Actually, I don't really understand why you are writing in your equation the fact that Cv dt over the big T over T should be equal to 0.
Yeah, because we are just at the beginning of compensation. If we are just above that, that's going to be positive. I'm going to gain some energy. Below that, I'm going to lose some energy. Yes. Yeah. I'm not losing, I'm not gaining anything, so it's 0. Yeah, no, it's yeah, you're right. But you can do a better analysis, but okay, it's a simple vision. You're right. You can go into the details, well, okay. So that's a simple thing. Okay, so yes, you have this curve. So the temperature and ρ, and above this line, gains are larger than losses, and below this line, gains are lower than losses. So this is all the shots that were done on NIF. It's about 170 shots, so we call that shot, but it's an experiment. 170 ignition experiment. Most of them didn't go through this line, but this one. That's the result of the last shot. That's where it's seated. But so you see the difference. Something happened, clearly. But that's the 170 shots we did on NIF, and that's the last one. So there is no question. There is ignition. So even if you talk about the political definition, from this point of view, you got ignition. You were able to have a hotspot for which the winds balance the losses, and even more, you can show that you have a beginning of thermonuclear burn propagation. We have proof for that. Okay. I'm quickly talk about that, so don't mind all these equations. So there is different ways to show that we have ignition or not, and different definitions. And this is one. So that's that's what we call ITFX. Don't worry about that, and don't worry about the way it's written. Basically, it's just a metric to measure how far we are from ignition. So we can get ignition, but how far we are, as we are really in a regime, or we are really robust, or just at the beginning of it. And this definition is made for ITFX is equal to 1 when we get ignition, just at ignition. And this was based on theoretical analysis, but mainly fitted on simulations. So they did in this paper thousands of simulations, and they look at we get ignition, we don't get ignition, etc. And they came up with this curve, which is pretty nice. If you put the number for this shot, this is where you are. So yes, you are just above ignition. So yes, you are at ignition, but you can feel that you are just at the beginning. So you are in this cliff, so it's going to be pretty sensitive. You understand that it's going to be pretty sensitive because you are just here. What you want to do is just be here, where it's flat, where it's more robust. So far, we are here. Okay, so I'm going to pass through that. It was just the, okay. So now I was saying, okay, no equation, we get ignition. But I was talking about what jet was saying. So 59 megajoule of energy, how it compares to this thing. Clearly, you got ignition too in jet. That's the same. So what's the difference? So the temperature for the experiment I was talking about, it was in September. No, sorry, it's February. It was 10 keV, about the same for NIF, sorry. The density was super small, as I was saying, because it is in big volume. The confinement time was about 5 seconds. And interesting enough, the DT mass was 0.17 milligram. Exactly the same, or basically the same as what we got on the shot on ICF. So it's because of the density are completely different, but the mass invested on these two experiments are pretty similar. And you got 59 megajoule of fusion energy and 1.3 fusion energy delivered here. So it's about, so what's the difference? The difference is coming from the power. If you divide the energy you get from the time you get, so 5 seconds for 100 picoseconds for fusion ICF, that's completely a different story. So the power is just crazy. So if you want to make a comparison, the magnetic fusion is more like a slow and stationary fusion, like the sun, to burn gently your thing, and that's okay. If you want to compare with ICF, it's completely different. It's completely fast and violently unsteady. It's like a supernova. It's the end of a star, so you are exploding and you have burn propagation. It's completely a different regime. So that's the reason why it's more easy, so far, to create a power plant from magnetic fusion than for ICF, because it's steady and it's easy to maintain, and etc. Okay, so why we had to wait about 50 years to get there? Why? Because since the 70s, we were talking about ICF, and people were saying, okay, we're going to do fusion with big lasers. Why it's so hard? Why we had to wait such a amount of time, 50 years? My point of view is that there is 4 main reasons. So it's because physics and technological complexity. So the first one is laser plasma interaction and instability. So you want to get your laser energy inside your capsule or inside your can, I was saying. And it's not that easy. So the plasma won't couple as you want with the laser. So you're going to have some backscatter. You're going to lose some energy because the laser is not going onto your capsule. You have also, so that's exactly what okay. You have also hydrodynamic instability. So that's the impression I was showing you before. On this simulation, I put some little perturbation. You don't see anything. You're going to see something soon. Okay, it's growing. So just a little perturbation at the beginning is amplified like crazy by your implosion. So, and you can't afford any type of perturbation. For example, the Eiffel Tower on the side of the Earth, you can't afford that. It's too much. So you need to be better than that. So better than the Eiffel Tower on the side of the Earth. There is another thing, it's the devil is in the details, so everything matters. So you need to control your laser energy, you need to control your roughness, you need to control everything at the % level, because everything matters, it's super hard. So that's really the technological complexity of it. It's everything matters and everything is super hard to control. And there is a last one. You really need, you really need cutting edge diagnostics. Because you do an experiment and it's failing, you don't know why. You need to measure things on the scale of tens of picoseconds. You need to measure millions of degrees. You need to understand image of neutrons, of X-rays with 10 keV energy. So it's super hard, and you really need time to develop cutting-edge diagnostic to understand what happened and correct your experiment and do the feedback. That's the 4 main reasons it was a hard thing. Okay, so how did we get there? So that's the experiment I was talking about. So that's the energy as a function of the experiment, as a function of year. So the NIF was starting in about 2010, 2011. And that's a different campaign. So if I remove this one, which is clearly an outlier, this is what you get. And it's clearly an incremental process. So you see you have plateaus, and you understand something, you have a new record, and you plateau for 1 year, 2 years, and you need to dig into that, you need to understand. And you do another plateau, oh, great, we understand something. And you do that. That's really an incremental process because that's the feedback. You're creating new diagnostic, you understand what happened, and you need 1 or 2 years to correct. That's basically what's happening. And it's even better if you do a log scale, you clearly see those plateaus. Okay, so it's going to be short. Okay, so I'm going to show you how we evolve as a function of time. So you can write that the neutron energy production, trust me, can write like that. So you have 4 physical parameters. It's 1D parameter. You think that you are ideal 1D implosion, and your yield or your neutron production depends on the scale, S. Obviously, if you have something larger and larger, okay, you have more production. Depend on the velocity of your implosion, so the way it's imploding, because it's kinetic energy, and you're going to transfer this kinetic energy into internal energy. Let's give you this thing. So depend on this guy, obviously. Depend on the pressure you put on it. That's the limit condition, the condition limit, which gave you due to the X-ray emission. And it depends on the way you put some entropy in your system. So if you put too much entropy, you won't be able to compress enough your system. That's going to be hard, so you don't want to put too much entropy. So that's what we call the adiabat. That's a measure of entropy. Okay, so you can write that the yield depends on a combination of this thing and depend on R parameter. I'm going to talk to you just a little bit later. Yes, so that was the 1D. So now I want to model something that go from this 1D to a 2D or a 3D perspective. So the world is not 1D. Okay, so I'm going to model that, and we're going to say, okay, I have a multiplier here, and which is 1 minus Q, which is the amplitude of my perturbation, and R, which is a model of my perturbation, and at a given power. Okay, but actually this guy, this perturbation, depends also on the 1D parameter. So you can revert your equation and write this equation depending on this guy. So that's my parameter which depends on the 1D parameters, and I can write the yield like that. And instead of this curve, I have this something like that. Okay, so again, Q is just a metric to the global technological control of the system. That's just the amplitude of the perturbation, the perturbation from the 1D implosion. Okay? If you have a perfect 1D implosion, Q is equal to 0. Okay? And you have this dependence. So, and you see that if you increase with Q equals 0, if you increase this or this risk, you have more and more yield. It's exactly if you increase the scale, for example, or if you increase the implosion velocity, you have more and more yield. But the thing is, if you increase the implosion velocity, you have also more and more instabilities, and you're going to be killed by that. So there is kind of a sweet spot between these two guys, and that's exactly what this thing is showing you. Okay, so, and if you change the quality, if you manage to have a better quality in the sense that you have less roughness or less power imbalance or whatever, you can move this curve around because you changed the Q. Okay. So that was the 1D design at the beginning of NIF. So it was super aggressive. They were supposed to deliver more than 10 megajoule. And that's what they got at the beginning. So you see the difference between the 1D design, what they were thinking they're going to get, and what they got. And it was because of that. It was too much aggressive, too much implosion velocity. It was too low adiabat. Okay, so. And that's exactly the shot I was showing you before. That's the first result. So when they did that, and during 2 years scale, we understand that we needed to change something. And we understood from diagnostic and other things that it was the hydrodynamic instability that were killing us, part of it, not only that, but part of it was due to that. So they changed the design, say, okay, we're going to trade, say that's not going to be as aggressive as before, but we're going to manage, and that's going to be better. So our 1D design is just a little less aggressive, and that's what we get. And this is what they got. So it was less aggressive from a 1D perspective, but it was much better in the lab because it was more stable. And that's what they get. So when we did that, you can ask the question, okay, it's better, but it's far away. It's still far away. It's order of magnitudes of what it should be. So maybe we are missing something fundamental. We are missing really something in the core of your simulation of our understanding. So that's the reason why we try to do a super no risky shot. So it's what we call this guy. So it's super low velocity, super low key implosion, low convergence. But the question is, can we get a 1D implosion? If you know that there's going to be a super safe implosion, can you really get what you expect in the lab? That's the question. And it was pretty great. So that means that there is no big missing part, no fundamental physics. It's just that we need to manage the robustness and the performances. We need to manage all these little features that are killing us. But it was interesting to see that. So after that, we changed completely. We changed a lot of things. We changed the all-room. We changed the ablator and changed different things in the things to go to this type of design. So it was better, but it was really much safer, and it was great improvement. So in terms of yield, it was maybe a factor of 2 from that, but it was really much better because the agreement between the expectation and what we got in the lab was much better. And from that, you can understand and build onto that. And after that, we went onto this direction. So improving a little bit the design and got some nice results. And for the last shot, it was even more aggressive. We went onto that. But the really thing that changed on this shot is not that. It's not the fact that we improve a lot the quality. So we started to understand what's going on. We fixed some issues, but we had to fix also, as I was saying before, the technological part. So the little feature, the little details that we need to fix. And when you did that, yes, okay. That's one of the things we fixed, but I'm going to pass that. And that's what we got. That's basically the story. And that's what I was saying. That's the balance between robustness and performances. You need to do this balance and understand and move from that. So the shot I was talking about, which name is N210808, is really the product of the incremental progress accumulated during the past 10 years in terms of physical understanding and theological control. So now, what are the implications of this result for the ICF community? So the first thing is, we know now that ignition can be reached on a 2 megajoule laser. No fundamental hurdle, no fundamental problem. And that's not nothing. 1 year ago, people, even in US, were saying you will never get ignition on it. You need 10 megajoule of laser energy. It's too complicated. It's too hard. And now we have the proof that we can. That's just great. The thing is, that's true, but 2 megajoule of laser energy is not enough. It's a beginning, but you also need a super great laser control, a super great technological control, and super great diagnostic control. Without that, you can succeed. So what are the next steps? So the first thing you can ask or say, can we reproduce this shot? So that's the first thing you did once. Can you do twice? Okay. 5 attempts, 5 failed of this shot, of repeating this shot. And to be honest, that's not really a surprise. I was showing you this curve. We are really in the cliff, so no surprise that it's super hard to reproduce this level. But even if we didn't reproduce exactly this shot, we have reached a new plateau. Again, that's a new plateau, and we understand something, and that's going to be better. We have, yes, so we can think that we're going to improve, and that's basically what Livermore or NIF is trying to do now, is try to push the design, try to push as much as they can the NIF as is without changing the laser energy or trying to build another laser, trying to understand more and try to do better. Okay. And the nice thing about this thing is there is a paper of the Academy of Science in US written in 2013 saying that the appropriate time for the establishment of a national coordinate broad-based fusion energy program within DOE will be when ignition is achieved. So that's changing things. So they got ignition, and now we can think about, oh, maybe we can think about doing inertial fusion for energy and see what we can get. So there is some designs. There is a lot of work to do. So we are really far from magnetic fusion, so really, really far. So magnetic fusion are talking about the ITER and demo, and they already have a path forward. We don't. We have some ideas, we have some designs, but there's a lot to do. But that's the beauty of it. That's just the beginning. So if I should sum up, because I'm just in time. That's just the beginning of a new adventure. We just got ignition, and everything is to be done now. So it's just not the end of the story, it's just the beginning of the story. So for the first time you got ignition, and now we'll see what we're going to get. And I'm going to leave you with my last slide, conclusion slide.
Thank you, Laurent.